Hi class. In this lecture we want to talk about the second part of Chapter 16, where we talk about different stages of star birth. So we talked about where stars are formed and how do we know they're formed there, and what we see, but what are some of the stages as to how stars are formed in the first place? So we talked about how this cloud of gas can be contracted by gravity, and it can break into fragments, and you can get, because of all the random motion in there, you can get gravity contracting different regions in different ways, and a big cloud of gas can ultimately form a bunch of stars, a whole cluster of stars. So let's look at this contraction again, and what kind of resists the contraction of gravity. So we said that as contraction is squeezing the gas and dust, the energy, the thermal energy of the gas and dust is getting higher. We're getting a conversion of gravitational potential energy into thermal energy, into energy of motion of these molecules and dust particles and gas. And the molecules help by absorbing energy of motion. They collide with things and they absorb energy, and they re-emit that energy in the form of light. And also dust particles as well. They get warm as they rub against things, as they collide with things. They get warm and they emit light also in the infrared part of the spectrum. So different wavelengths of light are emitted by molecules and dust particles. And so this emission of light helps keep the cloud cool. It helps kind of regulate the thermal energy. It helps keep the thermal energy from getting out of control so that gravity can continue to squeeze the cloud. And so contraction eventually slows down though. Eventually the thermal energy gets so high, the thermal pressure gets so big that gravity eventually slows down, and ultimately gravity stops squeezing at some point when the thermal pressure balances it exactly. And then what we have is a star ultimately. But the process before that, before it actually becomes a main sequence star, before it has sort of formally begun nuclear fusion, we call that thing a protostar. So the protostar is kind of the young star, not quite a star yet, not quite a main sequence star. We want to look at the different paths, the different sort of paths through its life cycle up to this point, from being a gas, a big ball of gas, a big cloud of gas, to being an actual star. That phase is called the protostar phase. So we talked about how matter will fall into this young thing, this forming star, this thing called a protostar. Gas will continue to fall into it or onto it, and it'll continue to gain mass as long as that gas is there. Eventually, though, something either blows away that gas, and it could be another star nearby that has a wind of some sort, a violent stellar wind. These young stars tend to be very violent, and they have strong stellar winds as they're forming. So these protostars, I mean, and they could blow away the gas and dust around other protostars around them, and that could stop the formation process. So once you've run out of gas and dust around a protostar, then it just has all the mass it's going to have, and it just continues to form. So we'll talk about that process. We also see rotation. We've talked about this before with the formation of our solar system. As this cloud of gas and dust collapses, it generally is going to have some kind of motion associated with it. And it's not going to just simply collapse and remain a ball the whole time. It's going to collapse and it's going to start spinning. The cloud is going to contract, it's going to get smaller, and because of various random motions, the random motions of the clouds and gas as they collide with each other, the cloud is actually going to flatten and get smaller and spin faster as well. So the rotational speed is going to increase because of something called conservation of angular momentum. So this cloud originally had some kind of rotation associated with it, but as it gets smaller and smaller, it rotates faster and faster. So it's like an ice skater. If she's spinning with her arms extended, she rotates at a certain speed, but as she brings her arms in, she speeds up and rotates even faster. So the same thing happens to these clouds. As they contract, they rotate even faster. And then there's this flattening. Because of the random motions of these dust particles, molecules, atoms, and so on, as they collide with each other, they tend that random motion tends to start getting kind of dampened out, and you get more of a uniform rotation around the protostar, and the random motions become more circular, elliptical, or more orderly, and the up and down motions in and out of the disk actually are reduced as well, and the disk actually flattens. So we get this cloud that doesn't just contract from a ball of gas to a smaller ball of gas. Rather, it contracts to a small kind of ball in the center with a disk around it. And that material in that disk could continue to kind of rain down on this forming star. And we refer to that as an accretion disk. An accretion disk is a disk of gas and dust around something that is kind of spiraling down onto that thing, onto that star, or possibly onto a forming planet, something like that. So another thing we notice that we see in newly formed stars are these things called jets. And so there's a rotation to the disk, and we see that there are these jets of material streaming out along the axis of rotation. No one's exactly sure why this is happening, but there are some ideas that seem to make sense. And one of the main ideas has to do with magnetic field. When you have a bunch of charged particles, a bunch of stuff rotating around, moving around, you'll get a magnetic field from that. And that magnetic field may help to kind of channel some energy or some stuff outward along the poles, along the magnetic poles, which are often the same as the rotational poles in a sense. For the Earth, we talked about before how, way back in our previous chapter, we talked about how the Earth's magnetic poles are not quite exactly the same as the Earth's rotational poles. And that's more so because the Earth is more of a solid object. But a gassy object is going to have those poles more lined up almost exactly. So these jets seem to be streaming out of the magnetic poles. Somehow the magnetic poles are kind of focusing these jets of energy outward. And we can see these jets in photographs. Here's a photograph of a protoplanetary disk, a protostellar disk, if you want to call it that. This disk around a protostar. This could be a place where planets are going to be formed. And we see these jets streaming outward. And these jets often collide with other gas out here, and we see other objects. We can see light being emitted from things out here where these jets are slamming into them. Those had a name. They were called Herbig-Haro objects, named after people that discovered them. They didn't know what they were at first, so they just called them objects. But now they realize that they are associated with these jets coming out of these new stars. So there's this way of kind of exciting the interstellar medium, the gas, far away from a forming star through these violent jets that are coming out. Here's another example. This is your protostar in the center, and these are those Herbig-Haro objects, these sort of glowing things out in space very far from a star, but they've realized that these are actually associated with material coming from the star, the new star, slamming into the gas that's already out there in space, causing that gas to glow, and you can see the glowing gas. So what would happen if we had a protostar that formed without any rotation at all? If it didn't rotate at all, this is very unusual. This would be very hard to find. There's always some kind of motion in a cloud of gas that's going to cause things to rotate ultimately as the cloud contracts. So its jets would go in multiple directions, or it would not easily form planets, it would be very bright in the infrared, or it would not be round. Well, the jets would not form in multiple directions because the jets forming seems to be related to rotation. So if you don't have rotation, you're not going to have jets, it seems. So that probably is not right. It would not easily form planets. Well, that may make sense. If you don't rotate, you can't form a disk, and that's where the planets are formed, is in the disk, so maybe that's right. It would be very bright in the infrared. Well, it's already very bright in the infrared. These protostars are already very hot, and they're glowing in the infrared. They're giving off a lot of infrared light. And that's in fact how we see them, as we talked about in the first section of this chapter. That's how we see them, through those molecular clouds that seem to be dark. And it would not be round. Well, that doesn't make sense. If it's a cloud of gas and it's contracting it's contracting without any rotation, gravity's squeezing it to a point, roughly, and gravity is sort of symmetric. It's going to squeeze it into a ball. That's why the planets are round. That's why everything's round, it seems, that gravity is able to squeeze. So it probably would still be round. So the answer is that B, it would not easily form planets. So if you had a cloud of gas that had no rotation, you could form a star from it, but nothing would be rotating, and you wouldn't have a disk. It would be a different star different type of star, perhaps not, the mass might not increase as much. There could certainly be differences. The rotation seems to do a lot of good things for us. So ultimately, how does nuclear fusion start? Eventually, this is what has to happen to make a new star. So the protostar, it looks like a star sort of at first because it does look bright, and we can plot it on the HR diagram. We can talk about its temperature and we can talk about its luminosity, and we'll do that. We'll look at an HR diagram in a minute. And that thermal energy that it has, the heat that it has, though, is coming. The light that it's giving off is coming not from nuclear fusion, but it's coming from the fact that gravity is squeezing this gas, and you have a conversion from gravitational potential energy into thermal energy, and that's why it's glowing. That's why it's giving off light, because of that thermal energy, not because of nuclear fusion. And gravity must ultimately squeeze this thing even tighter so that the temperature rises enough to start nuclear fusion. And so eventually gravity is going to have to kind of keep fighting a little bit harder and kind of fighting that thermal pressure to contract the new star enough so the temperature gets to about 10 million Kelvin or so, which is about the threshold to start nuclear fusion, turning hydrogen into helium. Ultimately, that's when contraction will stop, when there's a nice balance then between that outward pressure from the energy produced in the core by nuclear fusion and the inward force of gravity. Eventually, the contraction will stop when nuclear fusion starts, roughly at that point, and you'll now have an actual main sequence star. So when we look at an HR diagram, remember that what we're doing is we're plotting temperature on the horizontal, and temperature goes down as you go to the right, I mean. And luminosity, brightness, true energy output goes up as you go up on the left, on the vertical axis. So a cloud of gas is over here. A cool cloud of gas is over here. Very low temperature, not very bright. And so you can kind of imagine it plotted on this sort of extended HR diagram. And as this thing contracts, it gets warmer and warmer and brighter and brighter. And so it kind of travels along a path. It travels to the left, getting warmer, and it travels upward, getting brighter. And eventually, so it says here, a protostar assembles from a collapsing cloud fragment. It is concealed beneath a shroud of dusty gas. All right, and eventually, that dusty gas gets kind of blown away to reveal the actual protostar. And as the protostar shrinks, it continues to heat up. Gravitational potential energy is converted into thermal energy. But then something interesting happens. The temperature actually starts to become fairly constant on the surface. About 3,000 Kelvin. The temperature maintains, it kind of stays that way for a little while. And it's during that time that the interior of the star is entirely convective. And if you remember, we talked about this back in Chapter 14. And we talked about the sun and the different layers of the sun inside. And there's a convection zone, there's a radiation zone. In this convection zone, energy is being absorbed from below by gas. Gas is absorbing the energy and moving around more rapidly. It's not just re-emitting the energy. It's kind of holding on to the energy. And so the gases are getting hot and they're rising to the surface. It's like a pot of boiling water where the water vapor is rising to the surface. And so that's convection, where the gases are rising up, releasing their energy and coming back down. During this process, it turns out that the temperature of the star at the surface remains roughly constant. This is this new protostar, not quite an actual full-fledged star yet. But the temperature remains fairly constant at the surface when there's convection inside the star. And at some point, though, the temperature continues to rise inside, and at some point, the gas gets so hot inside that it starts to become ionized. The electrons start to get ripped from the nuclei, and when a gas becomes ionized, it can't absorb energy as well. It doesn't have a sort of a way to hold on to the energy in a sense. And so the light energy, just kind of starts passing through it, and that's where we get what we call radiative transport of energy. That radiation zone inside the sun is an area where it's really hot, so that atoms are fully ionized, and they just don't absorb the energy. The light just kind of travels through that region. It might bounce around as it goes out, but it doesn't necessarily get absorbed. It just kind of bounces back and forth, zigzags out on its way out. We call that the radiation zone, radiative transport. When that happens, then the surface of the star can actually start warming up again, and the star kind of continues to sort of travel to the left on this diagram, and it's continuing to contract. It's contracting the whole time. It's getting smaller the whole time. But the luminosity starts to increase now because it's getting hotter and hotter and hotter. And at some point right around in here somewhere, it does finally get hot enough for nuclear fusion to start, but there's just not enough nuclear fusion to prevent further contraction. So the star continues to contract, and as it contracts, it does get a little bit dimmer as the temperature increases. And as the temperature ultimately reaches a point where nuclear fusion is high enough, the rate of nuclear fusion is high enough, then it can stop gravity from contracting, and we finally have a nice newborn star on the main sequence, living a nice happy life for whatever amount of time, depending on its mass, several billion years or maybe just a few million years, depending on its mass. So just going through those again really quick, initially luminosity and temperature grow as material is collected into this protostar. And then at some point, when convection is the primary way of moving energy around inside this protostar, the surface temperature, it turns out, remains fairly constant, about 3,000 Kelvin. The star continues to contract, so it's remaining roughly the same temperature, and it's getting smaller, so the luminosity is going down. And then at some point, the star gets hot enough on the inside so that atoms start to become ionized, and they can no longer absorb energy, so they can no longer, kind of take energy to the surface. Energy just travels to the surface as light, and it bounces around. And during this time, then, the temperature again continues to increase as gravity is squeezing, and the whole thing still continues to contract, but now the temperature on the surface can start to rise again, and the luminosity starts to go up. Temperature is increasing, it's going to the left. Luminosity is increasing because it's kind of going upward. And then finally we can have nuclear fusion beginning inside the object, inside this protostar. And initially the rate of nuclear fusion isn't high enough to prevent gravity from continuing to contract the star. But eventually, after not too much time, the nuclear fusion rate becomes high enough as the temperature gets higher that there's a balance. There's a nice balance between the outward pressure from the energy produced by nuclear fusion and the inward squeezing of gravity, and then you have a nice stable star that is turning hydrogen into helium at a fairly continuous, a fairly constant rate inside. So that's the kind of the track that a protostar follows along on this HR diagram as it turns into a main sequence star. It does some zigzags in here and becomes ultimately a star like our sun in this case. So different stars travel, they're born in different ways. The most massive stars travel, and by traveling I'm not saying they're actually moving through space, I'm saying that we can plot them on this HR diagram, and they travel on the HR diagram as they change their temperature and as they change their luminosity. So a really massive star travels, in a sense, almost horizontally. It just continues to get hotter and hotter and hotter, and the luminosity stays fairly constant as it becomes a main sequence star. And that process for the really massive stars could take just 50,000 years. The process for a star like our sun could take about 30 million years, and it has a more kind of zigzaggy path to becoming a star. So the lower the mass, the longer it takes. The higher the mass, the faster it is. So more massive stars do everything faster. High mass stars are born faster, they live their life much faster, and they die much quicker. And so in a cluster of stars where all these different stars are formed at the same time, you've got really massive ones and you've got really low mass ones, you could have these really massive stars go through their entire life cycle, from birth through main sequence life, through supergiant phase, and ultimately forming a black hole or a neutron star, dying in less than the amount of time it takes for one of these really low mass stars to actually be formed in the first place. So you can have a cluster of stars where you've already got black holes and neutron stars that have formed, and you have many of the lowest mass stars not even fully formed yet. And so that is definitely possible. So high mass stars live their lives very quickly, and low mass stars take their own sweet time. They live their lives, they take a very long time to live their lives and to be born in the first place. So this section was all about forming stars, going from the gas cloud through these different phases of the protostar kind of development, and plotting those different kind of tracks on the HR diagram, and trying to understand at least some ideas behind how the star is changing its temperature and its luminosity, or how the protostar is changing its temperature and luminosity as it's trying to become a regular new main sequence star. Rotation is an important thing. Rotation helps form planets. You can't have rotation, or you can't have planets unless you have rotation. Conservation of angular momentum causes the gas cloud to rotate faster and faster. The magnetic fields also, I didn't mention this before, but if you read the book, the magnetic fields also play an interesting role in that they can interact with the disk. The magnetic field of this new star can actually interact with the disk, and it can actually kind of help transfer angular momentum from the rotating star to the disk material, and that helps slow the star down. It helps slow the rotation down. And so stars, when they're first born, they could be rotating very fast, but over time, through various processes, they kind of lose their angular momentum by kind of transferring it to other objects through various interactions, one of them being the magnetic field. And then nuclear fusion is ultimately begun when the temperature gets high enough inside the core, about 10 million Kelvin. And then once that happens, and once the nuclear fusion rate is high enough, it can balance, that energy produced can then balance the contraction of gravity, and then you have a nice stable star.